Hi. So in the last video, we wrote some Python code to do a very basic thermodynamic simulation in which we put particles in a box. Particles are free to collide at the edges of the box and with each other, so that even when the particles all start off with the same speed, after multiple collisions, they begin to form a distribution of speeds in which not all particles are moving with the same speed. And so in this video, we're just going to look into this a bit further and work out some of the variables associated with it. So if you remember from the first video, we discussed the idea of temperature. So temperature can be defined, the average, defined as being proportional to the average kinetic energy of particles themselves. So it'd be useful if we could actually work these things out. So this formula, then what we can do is we can go ahead and add these to our simulation. So where we have our simulation class, remember the simulation class contains all the particles, we can define average energy particles. To do this, we go over all the particles in the simulation, we then calculate its kinetic, it's the sum of all the kinetic energies, and then divide by the number of particles, giving you the average kinetic energy per particle. Likewise, we can then take that variable and calculate temperature, which is the 2/3 divided by the Boltzmann constant times the average kinetic energy. From that, check it doesn't break anything. It doesn't, which is good. And now, let's go ahead and be able to add that to our plot. So it'd be quite good if you could have some text somewhere that had this information. So the way the drawing works in Matplotlib is that to change the title, example text outside of the axis, it's computationally expensive. So it's the same situation we have when trying to change the axes on the bar chart. It's going to cause a slight hiccup every time it has to do it, so we don't want to do it that often. So we could update it sporadically, or the way in which I'll be doing it is to just set some text variables within the plot itself and then update them every frame. If we go to where we define the plots, we can add in two strings. So call it t_text, so that's temperature. We'll just do one for now. So that's temperature text. So it's the text object which is holding the temperature value. And when that's first initialized, it's a blank string. But we do that so it's created the text. And then in the update itself, whenever we update it, what we can do once the simulation's been incremented, we can go ahead and create a string for this. So it's an f string, so fast string. It's going to take the sim.temperature as given here, calculate that, 2 decimal places, and then return it in the same place. Have a look, and it's not worked. And that's simply because we need to come down to the bottom and tell the function animation that this value has changed. One of the things that's changed, and tell it to update it. And as we see, we have a problem here now. The temperature's coming out very, very large. And why is that? If we scroll back up, the average kinetic energy for these particles is going to be huge because it depends on the particle mass. Typically, when talking about atoms are very, very light objects, whereas what we've got here is essentially something billions of times larger. So we need to think of a way to solve that. And I think the easiest way to solve that would be to do something more realistic. What we can say is, let's go ahead and calculate temperature we'd expect, say, a xenon atom to have. So the mass of a xenon atom is 127 approximately. That's 166 e to the minus 27 kilograms. That's the mass of the xenon atom. And let's say we want this around room temperature. Remember from our plots here, at room temperature, a xenon atom has a speed distribution where most of the particles are between 0 and 500 meters per second. We go ahead, plug in room temperature, the mass of the xenon atom, and then where we create our particles, we can assign the mass. Now the particles have a mass to the xenon atom. And then for the speed, we need to calculate, we need to use this equation. Calculate what the average speed would be of a collection of xenon atoms at this temperature. All we have to do is rearrange this equation. If I go ahead, rearrange this equation, this is the value that we would expect. So we can go ahead, average. So now what we've done is we've given every particle in the box the mass of a xenon atom and the speed that a xenon atom, the average speed that a xenon atom has at room temperature. Next thing to change is we need to change our bar chart because we don't want it to go from 0 to 2 meters per second anymore. I want it to go from 0 to 500. We'll go with 10 steps. Let's have a look. Now we see it's going a bit crazy, but it's working. So the value of temperature that's been derived from the average kinetic energy of all these particles is indeed room temperature, so the temperature we plugged in. They are now moving very fast because they're very light, and they've got an average speed of 250 meters per second, simulating just 10 milliseconds is the, 2 milliseconds is not enough anymore. Go ahead and simulate every 10 microseconds. Now we get something a bit more realistic. Let's make that add quicker. The simulation is struggling a bit now because there's quite a lot of particles relative to, so it's doing quite a lot of calculations during each step of these animation frames, and Matplotlib isn't particularly known for its speed. But we can see we are indeed getting distribution we expect. Most of the particles between 0 and 500 meters per second, the peak around 200. Now what would be good is can we compare this bar chart to the theory? If we go back to the Wikipedia page and look at here, it gives us a Maxwellian distribution for particles, it gives us the Maxwell distribution in terms of a particle speed. So it's saying that given a mass of a particle and a temperature, you can calculate the distribution of its speeds. Let's go ahead and do that. If I find where this is, what we're going to do, we're going to put this curve on our bottom plot. Call it Theo, so theoretical curve is given by x, so x is going to share the same values as speed which we've got on the x-axis. What we do need to do now though is we need to change this linear space to an arrange. Rather than have 10 values between 0 and 500, we're going to have 0 to 500 in steps of 50. Then our distribution is going to reflect that. Complete it. Call the sim temperature. So this here, big long equation here, is literally just this equation written out. The appropriate mass, temperature. Go ahead and plot that, see if it works. And there we go. We can see the theoretical curve. And then our actual measurements from that particle in the box and how well it fits close to the theory. You can see it does fluctuate a bit because obviously there's a finite amount of particles. So we get a bit of jitter on there. As we can see, it is fitting very nicely to the theory. We can do one better. We could either increase the sort of number of averages, so how many frames it average to produce that bar chart, get it smoother, get it less get it less jittery, or we can increase the number of particles in our box. Increase the number of particles in the box, do a 100 frame average, see what happens. It will take a while, and the animation can be quite choppy when it's like this. As you see, evolving over time, now the particles are redistributing speed, and this is really nice because the equation for temperature is telling you that temperature is proportional to the average kinetic energy of all the particles. It doesn't tell you anything about the particles themselves. Maxwell-Boltzmann distribution tells you that in steady state, so if you have a lot of particles in an enclosed box, that there'll be a distribution associated with those particles. Whereas none of those theories are actually telling you what happens if, say, I just have a few particles at high speed, or one particle with high speed, or all the particles moving at the same speed. It's not telling you how it evolves. Now, you can do that. There is the Maxwell-Boltzmann equations that will tell you how systems like this evolve over time, but this is visually seeing that, so you sort of get a deeper understanding of the physics involved, which I think is really useful, especially when you're learning thermodynamics for the first time. This is really nice, a nice way to see it, to actually get a deeper understanding of what's going on. And there, as we can see, with more particles and better smoothing, it starts to conform to this theoretical curve more and more. And since we've got a larger number of particles, let's go ahead and change the bar chart to be finer. Even finer. We should start seeing everything converge. If we had an infinite number of particles or a finite amount of particles with a lot of smoothing, a lot more smoothing, we should see that curve and the bar chart, the diagram, start to match up perfectly. And there we go. Now I've got a bit of a problem here, is that the bar chart can go off the page. Let's try and fix that quickly. Where we said if the difference between the maximum bar on the bar chart is greater than 10 away from the maximum of the axis, then change it to the maximum of the axis. What we try and do is make this always bigger. How that goes. And it evolve over time. But even though all the particles started off with the same speed and in the same direction, actually, there's some finite amount of time, they all start to collide off each other, collide off the box, off the walls. We see it starts to form a nice distribution of speeds. So I think that's where I'll leave this video. I think if I do another video on this, it's going to be looking at some more of the interesting situations, such as giving one particle all of the energy, for example, or giving just a few particles all of the energy, so that the temperature remains the same, but the system is completely different. Thanks for watching.